So, let us do an example. Suppose there is a field biologist who is trying to study the character of a specific species of fish, and she is interested in knowing, are the males bigger than the females? Now, you know that there are some species in which the females are bigger than the males, in some species they do not have any difference, in some species males are bigger than the females. So, in this particular one, she has to get an idea of whether she can make the statement that the males are bigger than the females. Now, for that, if she were able to collect all the fish and measure them, then she would get a correct idea, but she cannot do that and she has to take samples. Now, suppose she has taken the following samples: adult male fishes, of the particular species, let us call it adult male, and we are trying to figure out also the adult females. Adult female. Now, we will need to know the sample size we will need to know the sample mean. She has collected samples and getting the mean is not a big problem. So, she has collected and obtained the means and also sample standard deviation. These are the data she has collected. The number was 95, 113 4 grams and 11.92 was the standard deviation, and in this case it was, he got a larger number here, 108.9 and 10.07. Now, we are trying to figure out this character. Again, we have to clearly state what is the null hypothesis. Null hypothesis again will be that the mean of the adult male is equal to mean of the adult female. We should not start with assuming the alternative hypothesis, and the alternative hypothesis will be, of course, the mean of the adult male will be greater than mean of the adult female. And we have to start with this assumption. We have to test whether we have enough justification to reject the null hypothesis. Okay. So, how do you do that? In this case, we know that it will be if we did this experiment again and again, that means we collect different samples every time, and every time we obtain the sample means, and the sample the difference of the means will be distributed in a normal distribution, because the number is larger than 25, and the standard deviation will be, so this is 0 if H naught is true. So, we assume the H naught is true, therefore, this is 0, the mean is 0, this is true, and the standard deviation in this case, this will be the estimated standard error which we can calculate as square root of this square. So, S E square by the number E plus S C square by the number C is equal to square root of S E is 11.92 square by 95 plus this is 10.07 square by 137, and this when calculated yields 1.495. Therefore, the test statistic is x this one minus this one. So, x adult male bar minus x adult female bar, this is the test statistic, divided by the ESE, that will be the Z. Now, this is x AM is 13.4, 113.4 minus 108.9 divided by the estimated standard error was 1.495, that yields 3.01. Now, 3.01 which is bigger than 1.96. If it is bigger than 1.96, then it is very unlikely to get a value of Z like this if the null hypothesis is true. Therefore, we can state with more than 95% confidence, we can state with greater than 95% confidence that the null is false. If the null is false, then we basically assume that the alternative hypothesis, which says that the adult male is bigger than the adult female, that is true. Okay. So, this is how we actually do the test. Now, the above method where we use the Z table to take decision regarding the acceptability of the null hypothesis, that is applicable to situations where we are able to take at least 25 data points for each group. Normally, this would be so, and that is the usual method that is used. But there can be situations somewhat rare, but there still possibility exists that there would be situations where we are unable to take 25 samples. So, when we were unable to take 25 samples, because suppose the disease is rather rare, so many people afflicted with the disease are not available in an area, or so there are various possibilities. For example, you are testing a hypothesis for which collecting each sample is very expensive, labor intensive. So, there has to be proper justification as to why you fail to collect more than 25 samples, but suppose you can justify that because there is a valid justification existing. In that case, we would not be able to use the Z table, because the distribution of the sample, the differences of the sample means will not follow the normal distribution. In that case, similar situations arose when we were studying measurement, where we are unable to take 25 measurements. There we saw that in that situation, the t statistics becomes useful. Here also we will use the same avenue, the t statistics will become useful. So, in that case, if the number of samples is smaller, for example 10 or 11 or something like that, then the number of samples also becomes a something that we use in order to infer something in the test from the statistics. While in case of the Z statistics, if the number of samples is more than 25, then we assume that the distribution is normal, and therefore, we do not need to use the number. But in case of the t statistics, we do need to use the number, because for each degree of freedom, the distribution will be different. So, in this case, the methodology, the approach, everything remains the same, only we have to use the t table instead of the z table. And in this case, so when the number of samples is less than 25, then we have to use the t table. So, the t statistics, t, that is what you have to use. And in that case, we have the way we obtain the z, we obtain the value of t, and the method is the same. So, we use x e bar minus x c bar. Any one could be bigger than the other. So, this could be a positive value or the negative value. In order to get a positive value, we put a mod. So, we get a number here, and then that has to be divided by the estimated standard error. So, this is how we obtain the z value, this is how we obtain the t value also. But now we have to consult the t table, and the t table demands that we use the degree of freedom, we specify the degree of freedom. Now, in this case, the experimental group had n number of samples, the control group had say m number of samples. So, the degree of freedom in the experimental group is n minus 1, and the degree of freedom in the control group is m minus 1. So, you have to add these two, m minus 1. So, that will be n plus m minus 2. So, that will be the degree of freedom in this case. And on that basis, we consult the t table and we take a decision, and we have already seen that in the t table things are given in terms of the degree of significance, which is 1 minus the degree of confidence. So, we will work out an example, and on that basis we will see how this is to be applied. So, let us go to an example. Let me erase this and let us go to an example. Suppose somebody has proposed that a herb relieves a certain kind of disease. So, for example, blood pressure in humans. So, a particular herb reduces the blood pressure in humans. So, the hypothesis is a specific herb reduces the BP of humans, and therefore, we are trying to test whether that herb will be useful in case of hypertensive patients. And suppose you have been able to collect total 25 patients. This will have to be divided into the experimental group and the control group. So, 25 patients by itself does not suffice. So, suppose we divide into the experimental group and control group. The experimental group has 12 patients, and the control group therefore has 13 patients, and we are doing the test accordingly. So, what we will do? We will apply the herb on the people in the experimental group for some period of time, and we will give a placebo which is similar to the herb, but not the herb itself, to the people in the control group, and then after some time, as hypothesized by the hypothesis, we will measure the blood pressure. And suppose after having measured the blood pressure of all of them, we take the mean, we take the standard deviation, and suppose the results come out as follows. The results, experimental results, they came as follows. XE, this is the mean of the experimental group, came out to be the diastolic blood pressure came out to be 81, and for the standard deviation of the experimental group came out to be 2.3, and the control group's average came out to be 83, and that came out to be 3.4. It is clear that the mean value for the experimental group is lower than the mean value of the control group. So, it appears that the herb was really effective in reducing the blood pressure, but let us check whether this particular conclusion stands on statistical scrutiny. So, in that case let us proceed. We have to first state the null hypothesis and the experimental hypothesis based on the way the test is conducted. So, the null hypothesis H naught will say that the mean of the population should be equal to the mean of the control group. So, this is different, this is for the sample, this is for the population. So, this is all the population of people which are who are hypertensive, who have high blood pressure, all this population, but having been applied with this herb, and this is not having been applied with the herb, the null hypothesis will say that they will lead to the same behavior, while the sample showed a difference. So, we have to check whether the difference is due to some random fluctuations. The alternative hypothesis will then be that mu E is not equal to mu C, right. And we are, as always, we have to root ourselves on the null hypothesis and check if we have sufficient ground to reject the null hypothesis. So, we then calculate the t value, which can be calculated from this. So, it is you have this is 81 x e prime minus 83, we have to take a mod of that, and then this has to be the in the denominator it is the estimated square error. So, estimated square error will be the square root of this number 2.3 whole square by the number in that group, which is 12, plus this will be 3.4 whole square by 13, and this turns out to be 1.7342. So, this is the t value, and now we have to consult the table, but before we do that we have to figure out what is the degree of freedom. The degree of freedom in this case was 12 is the number in the experiment group. So, 12 minus 1 plus 13 minus 1 is equal to 12 plus 13, 25 minus 2, 23, that will be the degree of freedom. And with that we have to consult the table. So, let us consult the table now. Now, here is the t table, and as you can see that these are tabulated in terms of the degrees of freedom and the significance level, and significance level is 1 minus the confidence level. So, 0.05 significance level is equivalent to 95% confidence level. And in this case we found that the degree of freedom is 23. So, we come down this row, this column, and come here, this is 23, and along this is the column for 95% confidence or 0.05 significance level. So, we come down this, and in the intersection we find this particular number 2.069. So, this is the value that we have to take now, and accordingly we go ahead with this 2.069. So, we were here, the value that we got, the critical value of t for rejecting the null hypothesis is in this case 2.069, and we have got the t value of 1.7342, which is below that, which means that the differences that we see is possible to get. This difference is possible to get even if the null hypothesis is true, because of the variability of the data, because of the variability as signified by the standard deviation. So, because of this, because of the random fluctuation of the data, if you repeatedly conduct the test by repeatedly taking different collections of 25 people, dividing them into 12 and 13 groups, then you will get these numbers as different, and they will have a distribution. The mean difference will have a distribution, and that distribution it is quite likely to have this number, this difference, as one of the possibilities in the distributions, which means that this is within a statistical variability of the data, even if the null hypothesis is true. So, we say the null, we cannot reject the null hypothesis. Notice that in the t table we have the degree of freedom also embedded in the table. This is important for use of the t table. Now, in books you will find that different techniques are applicable to different situations. For example, if the two standard deviations are the same, then what will happen? If the number of samples in the two groups are the same, then what will happen? There are all those details given in statistics textbooks. We will not go into that details. This is sort of an outline of the t method. For our purpose, we will assume that we will use the t table only sparingly, only in situations where we cannot use the Z statistics, only then. So, we will not get into the details of the t statistics. We will rather root ourselves on the Z statistics, but this is sort of a outline of how it is applied. For details, please refer to standard statistics textbooks. So, we will end this class here.